So this was the last thing we saw. If you remember, I had it drawn here. We saw that we had a robot in one specific configuration, still not things moving so much. What did we do? We started by attaching coordinate frames in each joint and then calculated transformation between each of the coordinate frames, and we figured out what is the overall transformation from the base until the end effector, and we used this one to calculate the position of the end effector expressed in the global coordinate frame, in the fixed coordinate frame, right? But I promised to you that we'll also see orientation, right? Because you asked for it. So what about the orientation? Basically, what happens if we just take the transformation matrix? 1 second. There's like too many things here. So what happens if I stop and I just take this thing, the transformation from 0 to 3, right? What did we see last week? We saw that this transformation matrix is basically this 4x4 is, we said something that it shows us something about rotation and something about translation, right? But what is this rotation thing that it shows me, okay? What this R03 tells me is basically how coordinate frame 3, the blue one, is positioned and oriented. So what is the pose, position and orientation, what is the pose of coordinate frame 3 as expressed on coordinate frame 0? Okay? Now, where in these numbers do we see rotation, or what are these 9 numbers that we see there, the zeros and the ones? What do they express exactly?
That we have no rotation.
How do you tell? That's true, we have no rotation because coordinate frame 3 and coordinate frame x, they are aligned. They don't have any change in their orientation. Okay, so x of the blue is aligned, is parallel to the x of the black. Y and z of the blue are parallel to the y and z of the black. So yeah, we don't have any rotation. The orientation is identical. But how can you tell? Basically, yes? Say.
We have the identity matrix, the rotation.
Okay, which we saw briefly last week that it shows us that, yeah, we have no rotation. But what if we had different numbers? How would we know, what is the orientation and what is the position? Basically, this 4x4 shows me, in a more general form, shows me several things. This 9 plus 3, 12 numbers. Okay, it's 12 numbers. These 4 here never change, so they don't add any information. They show me, what do they show me? Let's start with the easy part. Let's start with the translation part. What is this Px, Py, Pz? This is the, yes? On the translation of what? Of the coordinate frame, right? And more specifically, of the origin of the coordinate frame. So it tells me, if I have a fixed frame and another frame, it tells me what are the coordinates of the origin of the coordinate frame as expressed on the fixed frame. So let's call it 0, this is 1. So what is the coordinates of this point on this frame, on the 0 frame? Okay, this is what this tells me. Let's make it more general here. Let's call this M, and let's call this N, okay? So we use the same notation there. Okay, what is the position of the origin of frame N expressed in coordinate frame M? Clear? Clear. That's why, in this case here, you see here I have 0, 3, 3, because the position, the origin of this frame here as expressed on frame 0 is 0 on x, 3 on y, and 3 on z. Okay? Now, what about these 9 numbers showing me or rotation? First of all, how many rotations do we have? We saw 3 rotations, but I have 9 numbers. Okay, so here we will see that not all of these numbers are independent. I can change 3 of these and the other 6 are going to be defined by these 3. Yes?
I think it might be, each of the numbers might be somewhat the angle between one axis in one coordinate frame and the other, the respective axis in the other.
Very good. That's why you see here xx, xy, xz, yx, and so on. Different combinations between the 6 axes. I have 6 axes, 3 on one frame, 3 on the other, and here I have all the possible combinations of these 6 axes is 9 numbers. Okay? And let's understand what is each one of them. Basically, each row represents one of the axes of the, let's call this movable frame, mobile frame, okay? And each row represents one of the axes of the fixed frame, okay? And then I have the combination between the two. Let's start by the first one. Okay, so this xx, what does it show me? All these are projections, okay, of one vector on another vector. Okay, what is a projection? So if I have one vector and I have another vector, let's call this, I don't know, let's call this, whatever, I'm not calling it anything. What is the projection of a vector on another vector? Is basically what if I draw a line perpendicular, so I'm looking the projection of vector 1 on vector 0. Okay, I draw a perpendicular line from the end of vector 1 perpendicular to vector 0. Okay, the projection of vector 1 on vector 0 is this length. Okay, just the length. Okay, what does it depend on? How long this will be? The angle between the two. Let's call it, I don't know, theta. And what else? And the length of the first vector. Of course, this is longer, the projection will be longer, right? Now, what did we say about coordinate frames? What are the lengths of the vectors? We consider them to be unit vectors, so length 1, fixed frame, fixed length. Okay, we consider all the lengths of all these frames, all the lengths of all these frames to be, of all these vectors to be 1. Okay, so this will always be length 1. Okay, so then this projection here, this length only depends on the angle because I have a fixed length. Great. This relates to the cosine law, if you ever heard of it. Basically, if I have two vectors, I can calculate the projection of each based on the cosine law. Anyway. Okay, so the first element here, xx, as I said, the first column relates to the movable frame, the x-axis of the movable frame. Okay? And the first row relates to the x-axis of the fixed frame. So it's basically the projection of the x of the movable frame on the x of the fixed frame. Okay? The second element below it, it's the projection of the x of the movable frame on the y of the fixed frame. And the third one on the z of the fixed frame. Okay? The second row, the first element is the projection of y of the movable frame on the x of the fixed frame, y of the movable on the y on z. Okay? and the last column is z of the movable on x, y, z of the fixed one. Okay? Let's see now, why do we have the identity matrix when the coordinate frames are aligned? So if I have a frame here, and another frame here with no rotation, what is the projection of x-axis of the movable frame on the fixed frame? Basically, they're parallel, right? Do you see it? I mean, as I said last week, when I draw the x like this, it means it comes out of the board. So here I have a vector like this, and here I have a vector like this, both pointing towards you. Okay? So I have, I'll draw on this side. I have this, let's call it x of the fixed one, and I have x of the movable one. What is the projection? What is the length? If I draw a perpendicular line from the tip to the vector and I see that length, what will be that length? It will be equal to the length of the vector. And what is the length of a vector, we said? 1. It's a unit vector, so it's 1, right? So my xx is 1 because I have no rotation between the two, right? Let's see, what is the projection of x of the movable on the y of the fixed one? So I have x coming out of the board and y here. What is the angle between them? Let's take one step back. What is the angle between this x and this y? 90 degrees, right? If this is parallel to this, then it's also 90. So they're perpendicular, right? So if I have the y of the fixed frame and the x of the movable frame, what is the projection? I draw a perpendicular, so this is perpendicular. I draw a perpendicular line from here, to this vector, and I see this distance. What is this distance? 0, right? Basically, this projection is, what is this? If this is a right-angled triangle, what is this length? If this is 1, trigonometry, cosines of theta. This is sines of theta, this is cosines of theta. That's why when theta is 0, cosines of theta is, cosines of 0 is 1. And when they're perpendicular, cosines of 90 is 0, right? That's why this element xy here is 0. And the same with z. This x coming out of the board is perpendicular to the z pointing upwards. Okay? And the same with the other axis. The y of the movable one is perpendicular to the x of the fixed one, it's 0. The y of the movable is parallel to the y here, so they're, it's 1. Y with z, 0. Z with x parallel 0, z with y 0, z with z 1. Okay? That's in the case they are oriented the same way. Let's see very quickly one more example, because I see you're not 100% sure yet. Let's see. I have my fixed frame here, x pointing out of the board, y right, z up, And then I have another frame here, which points x downwards, z out of the board, and y to the right. So y points there, x down, and z out. Is it rule of the right hand? X, y, z. Okay? X, y, z, and then it's the same thing as x, y, z. Okay, so it's the same, just rotate it. Now let's figure out what would be the transformation between these two, just the rotation part. What is the projection of x of the fixed one, of the movable one, on the x of the fixed one? So x of the fixed one points towards you, we said. X of the movable points downwards. What's the projection? 0. They're perpendicular. Okay. X of the fixed one, y of the x of the movable one, y of the fixed one. 0, again perpendicular. And now, ladies and gentlemen, x of the movable one and z of the fixed one. Why? Why minus 1?
Because
180 degrees, cosinus of 180, minus 1. Very good. Okay? Y of the fixed one, x of the inverse. Y movable, x fixed. Perpendicular, 0. Y, 1, they're parallel. Y, z, 0. Zx, z pointing out of the board, x pointing out of the board. 1 minus 1 or 0? 1. Why 1? In the same direction. 0 degrees. 1. And this will be 0, 0. Okay. So this is how we codify orientation. Now I hope this answers your question finally after a couple of slides. It took a long way, but yeah. With these 9 numbers. Of course, it's not always 0 and 1, because if this was not perfectly aligned, but this is just to show you the idea, okay? If I didn't have 90 degrees with everything, it wouldn't be, the cosinus would not be 0 and 1, it would be other values. Okay? So this is how we code orientation of an object, by attaching a coordinate frame on that object that is rotating. The coordinate frame will rotate together with that object. And the position we saw, it's the last column, which expresses the position of the origin of this coordinate frame on the fixed coordinate frame. Clear? Great. So this is the projection. And what we've seen now is, this static configuration where we had this robot in this exact position, and we wanted to figure out what is the pose of the end effector. But that's boring, because we will not have a fixed position that we need to calculate. We could calculate it with a, linear, with a ruler. So what happens in more general configurations? Okay. Now we start adding variables. What would be our variable here? What is the thing that is changing? The angles. Theta 1, theta 2, theta 3. Which we start calling them joint coordinates. They're not coordinates the way you use them, but it's basically the values of the joints at every point. Okay? How do I calculate now that I have variable joint values? How do I calculate now the pose of the end effector or of my robot? Any ideas? Sorry?
The same way we did in the first example, but now we write the rotation matrices.
With variables. Not with fixed values. Perfect. That's the whole idea. Exactly. Very good. So what was the first step? L01. So we define, and to do that, I need to define first coordinate frames on each joint. Okay, so what George said, identify joints and put coordinates, put the coordinate frames. Okay, so I go and I add coordinate frames on the links. Okay, I try to keep the, now here you see better the idea of the coordinate frames moving together with the links, right? So you see the green coordinate frame, just turn on the laser, the green coordinate frame, the y-axis will always be aligned with this link. Okay, so if the joint rotates, then the coordinate frame also rotates the joint. Here again, the y coordinate will be aligned with this link. It could have been any axis that will be aligned with this, but you choose one, and it's easier if you just make it stick. Or it could have been any configuration as well. It could have been, I don't know. The idea is that this frame will move together with this thing. Imagine you have like a frame with straws. Did you use them in the lab, Joanna? Imagine those, and you just stick them on the link. You stick them, and then it will move together, right? Once we have this, what do? We calculate the transformation from 0 frame to 1, from 1 to 2, from 2 to 3, and then I multiply them together. Okay, let's have a look. What would be, in this case, the R01, where 0 is the black and 1 is the green one. Here I didn't put the numbers, but yeah. What would be the transformation from 0 to 1? A rotation and translation. What should I write first, the translation or the rotation? Who says the translation? The translation. Who says the rotation? The rest? Whatever. Why doesn't matter? Okay. Let's pick one. Pick one. I don't know. Translation or rotation?
I think we always use rotation first.
Okay, maybe.
It doesn't matter.
It doesn't matter. Let's pick one and see what do we do. Let's say translation first. You okay? Yes? Yes. Let's say translation first. So this, from 0 to 1, I'll have a translation first. What translation? Translation on Z by, let's say that distance is 1. Okay? Translation on Z by 1. Translation on Z by 1. So when I do this, colors. When I do this, I start from here and I go here. Okay, I just translate on Z. This is the black one. I don't have black chalk. This is the green one. Okay. Now I'm here. What should I do so I'm aligned with this one? You said something about rotation. What rotation? Around which axis? By how much? X by theta 1. So basically I'm rotating around this axis that comes out of the screen by this angle here, theta 1. Right? This rotation around this axis. The axis coming out of the screen. Great. Do I multiply from the left or from the right? Around which axis am I rotating? The fixed x or the movable x? So I should multiply from the left or from the right? From the left or from the right? From the right. From the right. You will get used to this. Okay? It's normal you don't understand it. It took me years to get it as well. It's mind-blowing. Okay, so from the right, because I'm rotating around the green axis, so the already transformed one. So I do this transformation, I reach the green axis, and then I rotate. If I want to rotate around the green axis, I will multiply from the right. And I will end up with a new coordinate frame. Let's use another color. That will be rotated around the x, so the x will not change. And it will look like this. Right? If I was rotating around this one, I would not have done this. I would have done this. So this. Okay, so I would have ended up somewhere here. You understand the difference? I would have rotated around here, not around here. So I multiply from the right. Sorry, to our listeners on YouTube. So rotation on x by theta 1. Great? Do we agree? Great. Now let's do it the other way around. Let's say I first rotate it, because there was this debate. Let's say I rotate first by how much and around where? So this is my fixed one. I should rotate by how much? Theta 1. Around which axis? Around x. And I would end up, just rotation, here. Okay, so r x theta 1. And then translation. Around which axis and along which axis and how much?
From Z.
Z?
The absolute.
Along Z by 1, okay? Which Z? The green one or the black white one? Around this one, along this one. So, can I finish my point? So, multiply from the left or from the right? From the left, because now I move along this frame and not this frame. By Z by 1. It's the same thing, right? Two ways to see the same thing.
We can also translate onto axis in a relative way, right?
Which means?
So we do the rotation first and translate onto axis of the green coordinate frame.
You can do it by multiplying.
Yeah.
So if you want on the green one, then you have to multiply on the right. Sorry?
That we more time.
Yeah, but then if you combine all these things, so you're saying moving on this one and then on this one. Yes, you could do this. The result will be the same though. If you do the multiplications, they will cancel each other out and you will end up with the same result. Try it at home. Yeah, you could go through Bucharest and come back here with transformations, and the result of the multiplications will be the same result. Now the question.
Shouldn't be the green x-axis parallel with the red x-axis if we rotate around?
Yes, it is. It's an artistic representation. Yes. Yes, that all the x-axis here, they come out of the screen. It's just a bit difficult to draw them, and yeah. But they are. Yes. Now, who said doesn't matter? He was correct. Who said first translation was correct? Who said first rotation was also correct? Everybody wins. You just have to understand, you know, if I do first rotation and then translation, how do I multiply things, along which axis am I rotating, translating, and so on. Okay? Good. So basically here, yeah, we have a translation and rotation around x. I will show you the results here. Then on the second one, I have the same, again, a translation and a rotation. Which happens first doesn't matter. Okay. You see them here? So this is the first translation on z. This is the rotation around x. Small thing, notation-wise. When I say C1, I forgot to add this on the slide. Cosinus of theta 1, we usually write as C1. Sinus of theta 1, we write it as S1. So we don't write cos theta, la la la. Okay, a bit more tidy. Okay, so that's why you see here C1, S1, C2, S2 is theta 1, theta 2. Basically, this is the transformation matrix for rotation around x by an angle theta 1. Okay, and the last one is again a translation and a rotation. Here, if you see, here I missed it. It's L1, not, no, here it's 1. Okay, this distance is 1. Then we have L1, L2. Okay, and again I can use this one to calculate, for instance, if I know the position of this point on this frame, so the end effector on this frame, which is these coordinates, I can use again the thing that we saw before the break to calculate the position of the end effector on the fixed frame. Now these R01, R0, R12, R23, they contain a variable, so they're not fixed frames, they're not matrices with specific numbers, they have variables. They have this cosinus of Q3, of theta 3, and so on and so on. Okay? So this position here, P0, is basically this matrix here, which consists of variables. Okay, see another notation. C1, 2 is cosinus of theta 1 plus theta 2. I think. Or times, don't remember. I'll double check this. Basically, I can calculate the position of P0. P3 is fixed because it's the position of the end effector on the blue frame. Okay? And I can calculate the position of the end effector for any value of theta 1, theta 2, theta 3. So if I know the position of my joints, then I can know where is the end effector. Okay? And not only the position, so if you remember, the last position is this one. The position is the last column of the 4x4 matrix. Okay? But I can also know the orientation. No, the point does not have orientation. Okay? Now, if I want to know the orientation, then I forget the points and I just keep the transformation matrix. Okay? The transformation from 0 to 3. This is wrong. Should be 3. 0, 3. Okay? And this shows me what the transformation from 0 to 3 shows me what is the position and orientation or pose. What is the pose of the last coordinate frame here in respect to the base frame here. Okay, for any value of Q1, Q2, Q3, theta 1, theta 2, theta 3. We're going to start calling joints Q1, Q2, Q3. That's why I'm. Okay. So this is the direct geometric model, the thing that I said in the beginning that we're going to talk about. We finally have it. Took us quite some time, but we have it. And this is what it does. It tells me the pose of the end effector or of another coordinate frame if I know the values of the joints. Now, I could do this for any point of the robot. I don't have to do it just for the frame here. I could put a frame wherever I want on a fixed point of the robot and calculate the transformations from the frame, the fixed frame until that point and calculate the direct geometric model for that point. Okay? So how could I calculate the position orientation of the end effector of the gripper? I would just need to put one coordinate frame here at the end and calculate also the transformation from here to here, which would be a fixed one because there is no joint involved. So these two are not relevant right now. Shall we see quickly an example in 3D? Very quickly. Let's see, because we just talked about 2 dimensions, but it's exactly the same idea in 3 dimensions. So you will see this kind of figures often. So it's better if we understand how they work. So when I draw like these diagonal lines, it means the thing is coming out from the board, okay, the axis. So here we have the coordinate frame, the fixed one, x, y, z, and I have a joint, first joint that rotates around q1, rotates around zeta, and I denote it as q1. So that's rotation around the z going around the axis going up. Okay. Then I have a length L1. Then I have a rotation around an axis that goes out of the board, q2. Okay. Then I have a rotation around an axis that is going to the right side, q3. And then I have another joint that rotates around again out of the board. Okay? So we need to put frames in each joint and calculate the transformation from the fixed frame until the end effector. Let's do this quickly. Let's say this is my fixed frame. I'm not going to draw the robot, I'll just draw the coordinate frames. So where should the first one be? We say we always put it attached to the link at the joint level. Okay? So the first one, we would put it at the link. So the first link is this part here, starting from here, going until the second joint, from the first joint to the second joint. So it would be something like this. Let's say rotate it. So this is something rotated around this axis. Okay? And it has an angle of q1. Can you visualize it? This is q1 as well. So it rotates like this. Okay. Then I have another frame, red, that is, let's say, like this. Sorry. Let's rotate it a bit. Okay, so this one rotates in this direction. Okay. Then if this one rotates, then the whole link will rotate, and the next joint will be like this and rotating. Sorry. By Q3 we are here, and this was Q2, not here, sorry, red, it should be Q2, okay, and let's do it until here, it's fine, you get the point. So let's see, now I put the coordinate frames, let's figure out what are the transformations between coordinate frames. So from the fixed one, 0 to 1, from 1 to 2, and from 2 to 3 in 3 dimensions. So what's the transformation from 0 to 1? What do I have? Rotation around z by q1, theta 1, q, let's call it q. Okay, from 1 to 2, a translation and a rotation. Now, first translation or then? So translation on Z. Translation on Z, let's call this rot by L1. Okay, and then rotation on X by Q2, left or right? Are we rotating around this Q or this Q? This X or this X?
The second one's like this.
Second one, so from the right. Rot X Q2. Okay, R2, 3. From here to here. Again, translation and rotation. Now you get the picture here, so I don't insist again. It's always translation and rotation in these cases. And then rotation around this axis. So let's say if this is y, this is y, this is at this x, so rotation around y by Q3. Okay? And I could do the same for the fourth one. It would be translation. Yeah, here the L2 you can split it until this joint, there, it doesn't matter, the lengths. But that's the idea. Even on 3D it's the same idea. We put the coordinate frames, we figure out what's the transformation between them, we sandwich them together. So R03 will be R01, R12, R23. Okay. And if I want to have for the end effector, then I have to add the coordinate frame here and figure out what is the transformation from the fixed frame until the until the end effector. Okay, and this 4x4 will show me the position and the orientation of the coordinate frame attached on the gripper, which is kind of also the position and orientation of the gripper itself. Clear? This is from Greece, by the way. I didn't bring it. It's from Halkidiki. I just saw it here. Questions? So one more example, but yeah. And this is the last slide in case you ask again. Any questions? No?